Well, thank you all for coming. It's amazing to see such a big crowd, especially consider the caliber of the speakers they have here on a weekly basis. My name is Fergal Mullally. I'm home on my holidays. If you notice, I don't have an American accent. I work with Kepler. I've been working with it for a couple of years, and I thought that while I'm back and you have no one else here to talk about Kepler, that I'd give it a go. The Higgs Boson today, which is that amazing discovery that everyone's talking about, it reminds us that science is about asking big questions. And if you're a scientist and you're stuck in a lab and you're trying to get a piece of equipment to work or you're trying to get some piece of code to work, you tend to forget this. But it really is, it's about asking about things like, where do we come from? What are we built out of? The one question that has struck me, being an astronomer, I spend a lot of time looking at pictures like this. We do actually take pictures like this once in a while. It's kind of cool. And you think about the distances between these stars, and you think about the number of stars. There's like 100 billion stars in our own galaxy. We look out deeper into the universe, there are more galaxies that we can see than there are stars in our own galaxy. And so you look at all this stuff, and the question that comes to my mind over and over again, the biggest question of them all as far as I'm concerned, is this one small little planet that we're living on the only one that has life on it? And it's up to you. If you don't find that an interesting question, the door's there. You're not going to enjoy the rest of the talk. Peggy Lee, I think, said it best. She would talk about something else, but she says, is that all there is? And we don't know. We've been asking these questions in the ancient Greeks, and we don't know. Is that all there is? We don't know if there's other planets out there like us. We don't know if there's planets out there with people with pointy ears. We don't know if there's planets with blue skin, super intelligent slimes, any of that stuff. And that's what science is all about, is asking big questions like that, and not just asking them, but answering them as well. And to put it into perspective, it's just how small and tiny this planet is. I want to show you this picture. This was taken by, I think it was one of the Voyager probes. It was out past Saturn, and Carl Sagan, who was the greatest public lecturer astronomer of them all, said, can we turn the probe around and point it at Earth and take a picture? And so they took a picture of the Earth. And I'm not sure if you can see it in this because it's so small and insignificant. There it is right there. That little speck. If you're at Saturn, that's what the Earth looks like. You wouldn't notice it. And Carl Sagan got very emotional about a lot of things. But I'm going to read this out to you because it's such a beautiful phrase. And he says, that's here, that's home, that's us. On it is everyone you know, everyone you love, everyone you have ever heard of, every human being who ever was, lived out their lives there. The aggregate of our joy and suffering, the thousands of confident religions, ideologies, economic doctrines, every saint and sinner in the history of our species lived there on a speck of dust suspended on a sunbeam. If I ever write anything that good, I'm publishing it. Now, as I said, we've been thinking about this problem since the ancient Greeks, and it's a very hard problem. The way to solve hard problems is to break them down into smaller problems. This has been done in many different ways. This is the one I'm going to do for you tonight. We're going to break this down into 3 questions. What sort of life would we recognize if we saw it out there in the universe? Where should we look for the sort of life that we would recognize if we saw it? And how would we find such a place? What sort of instrument would we have to build? Now, this first question is kind of subtle, because the universe is really big. The life we find on the Earth is enormously complicated. They found life at the bottom of glaciers. They found life inside of nuclear reactors. There's all sorts of complicated things out there. If we saw something on another planet, would we even recognize it as life? And the way around that is to say, well, maybe we wouldn't, maybe we wouldn't. But let's go looking for something that if we saw it, we would recognize it as life. And that simplifies that problem a lot. The answer to where should we look, just to give it away, is on planets a lot like our own, little specks of dust on sunbeams. And how would we find such a place? Well, the answer to that, you can probably guess, is going to be the Kepler Space Mission. So what sort of life would we recognize if we saw it? And basically, if you see pictures of these things, you recognize them as alive. We've got stuff that lives in trees, we've got stuff that lives in the water, we've got stuff that is trees. You want to look for things that are instantly recognizable. And I've boiled that down into 3 characteristics. Life that we recognize, life like us, it breathes air of some kind, it drinks water, and it eats some kind of food. Now, automatically, you can think of counterexamples to this. You can think of bacteria that survive in, like I said, at the bottom of glaciers. They don't seem to breathe any air. They seem to get along just fine. There's fish that live in the sea, right? They don't breathe air. They breathe water somehow. But we simplify it down. We've got these 3 questions. We can find stuff that looks like that. We'll say that that's life. And that turns out to be some of the easier life we can go to detect. Where should we look for something like that? And the answer is on planets like our own. And there's a couple of reasons for this. If you go to planets which are too big, stuff like the gas giants like Jupiter and Saturn, there's no rocky surface for which life to get a grip. If there's food, you eat animals, animals eat plants. Plants get most of their energy from sunshine, but they also need some sort of a rocky material to get the essential minerals, the potassiums, the calciums, and stuff like that you need to build bodies. On the other hand, if you go to a planet which is too small, like, say, the moon down here, there's not enough gravity there to hold on to an atmosphere, and so there's going to be nowhere to breed. And so you need something which is not too big and not too small. Another thing you have to be concerned about is the temperature. If you've got a planet which is too close to its parent star, it's going to get too much sunshine, it's going to be too hot on the surface, and the surface is going to be molten, it's going to be too hot for water to exist. All the water will boil off out of the atmosphere. You get a planet a lot like Venus. On the other hand, if you've got a planet which is too far away from the sun, it's going to be too cold. All the water is going to freeze to ice, and you're not going to find a lot of easily recognizable life there either. So you want to find something which is not too hot and not too cold, but just right. And so some smart aleck came up with the idea of calling it the Goldilocks zone. Now, when we go to conferences, us astronomers have to pretend to be, intelligent and stuff, so we can impress our colleagues and get jobs. So we call this the habitable zone. But I think the Goldilocks zone is as good a name as any. But through the talk, if you hear me say habitable zone, it's interchangeable with Goldilocks zone. I mean the same thing, and sometimes I slip back and forth. So, summarize the last two slides. We want to find life like us. We want to look for planets which are like our own. And we can boil that down to two key characteristics. They're about the same size as our own, and they're about the same temperature. Now, temperature turns out to be a little bit more complicated than what I've described here. If you work out the distance the Earth is from the sun and how much sunlight it's getting, and how hot it should be, how warm it should be on the surface of the Earth, you get a temperature which is something like minus 18 degrees Celsius. The reason for that is you haven't included the effect we have an atmosphere around the planet, and that is a greenhouse effect. And the greenhouse effect increases the average temperature up to about 14 degrees Celsius. So when we calculate the temperature with this somewhat naive prescription, we're probably always going to get a value which is quite a bit lower than the real number. But it's a ballpark. If you get a temperature which is hundreds of degrees Celsius, that's not very suitable. If you get a temperature which is very, very negative, like minus 50 degrees Celsius, that's probably not suitable either. So it gives you an idea. So we know what we want to look for. How should we go look for it? And you might think that it's fairly easy to find a planet. We've got all these big telescopes that have been invented. We've got the Hubble Space Telescope, which is, of course, in space. Can't we just point these at stars and go looking for the planets? And we stare for a really long time, we will see really small, faint things like planets. It turns out to be quite a bit more complicated than that. And it's a little bit more subtle idea than you normally like to explain in a public talk. And it's got to do with the issue of contrast. And the best analogy, the best metaphor I can come up with is playing a game of hurling. After moving to California, having never played the game for 30-odd years, I got drafted onto a hurling team. I'm a proud member of St. Joseph's of San Jose, California. I have been since March, and so I consider myself an expert in this subject. But imagine, if you will, you're out there, you're playing hurling, and the ball comes in, you've got your back to the sun, the sunlight is reflecting off the ball, and you can see it come down. And so as long as there's not someone trying to whack you with a stick, you can leap up and catch the ball. If, on the other hand, the sun's in your eyes, the ball's not any fainter, but the glare of the sun is so much that it's just going to blind you completely. It's not that the ball is too faint to see, it's that the contrast between the ball and the sun is just much too large. And this is the same problem as what we have when we're trying to find planets around other stars. So, to give you an idea of what's going on, this is what we imagine in our heads. We've got a very small planet, and it's in this nice orbit around this star over here. And you think, oh, just point your telescope, you'll see one going around the other. What we actually see when we look through our telescopes is something much more like this. The light from the stars is blurred out of a small bit of an area. The light from the planet is so much fainter that compared to the light from the star, you just don't have any hope of seeing it. It's really impossible to go and directly detect a planet like this. At least it was when I'm growing up. I'll get back to that. So we need another way to find planets. We can't image them directly. We can't just go out and take a picture. And people have come up with about 6 different ways of doing this with greater degrees of success or failure. The one that we've latched onto, the one that has proved the best for finding very small planets like the Earth, turns out to be something that we call the transit method. So to give you an idea of how this works, imagine that there's an alien astronomer and he's sitting at his telescope and he's looking up at the sun. And if he's at the right angle and he's really patient, every now and again one of the planets will just happen to pass slightly in front of the sun and block out a little bit of the light. Just like that. Now if you take Jupiter, which is the largest planet in our solar system, it's about 1/10 the diameter of the sun, so if it passed across the surface of the sun, it would block out about 1% of the light. It takes Jupiter about 12 years to go around its orbit once, so if we have a very patient alien astronomer and he watches the Earth for about 12 years, he will see 1% of the light taken out of the light of the sun twice in 12 years. So it's not an easy way by any means to detect planets. Now, if you think about the Earth goes around the sun once every 365 days, right? So you don't have to look nearly as long to find the Earth. You only have to look for a year or so. The trouble with the Earth is it's very much smaller. It's about 10 times smaller than Jupiter, and so it blocks out about 1% of the light from the sun. Of course, our alien astronomer could get unlucky, and instead of looking in the right plane where the planets happen to pass in front of the star, he could be slightly above or below that plane. And so the planets, as he sees them, never pass in front of him, and so he never sees anything. And that's how the transit method works. We go out and we look at a lot of stars at once, and we try to see a little bit of a dip when a planet passes in front of them. To give you an idea of what this looks like, this is a very simple animation of what I said. So you've got a planet, it's passing in front of a star, and of course the star, you don't see a disk. It's just like looking at stars in the sky, they're points. And so what you don't see the planet pass in front of the star, you just measure the brightness of the star. Brightness of the star gets a little bit fainter. And that's what we look at. It's very simple, really. It's also a nice animation. I like leaving it up there. Of course, animations never work in PowerPoint, so I always have a backup slide as well. Same idea. You've got a planet, it's passing in front of the star. The brightness of the star gets a little bit fainter as we see it. Now, this doesn't happen for if there was planets around every single star in the galaxy. We wouldn't see this something like 99% of the time because the orientation is wrong. You have to be exactly lined up. We have to be lined up with the orbit of the planet around the star. If we're off by like a couple of degrees, maybe 2 degrees, we just won't see anything. So if you want to find planets this way, you have to look at a lot of stars because you're going to miss 99% of the planets before you even start. So this is basically what we look at. So this is some real data from our telescope. And this is more or less all that we see. We're measuring the brightness of the star here, and you can see it's more or less the same. But every now and again, you get a little bit of a dip, here and here. Now, from the size of this dip, we can measure the amount of light which has been blocked from the star, and we can use that to work out the radius of the planet, how big the planet is. Based on the radius of the planet, we can kind of guess at the composition. Small planets, the ones that we've been able to measure the mass from other methods, turn out to be mostly rocky. In fact, all of them that we've found so far have been rocky. All of the ones that we've found that we've been able to measure the mass have been rocky. Being a scientist, you say things, you say, well, that's not quite right now, is it? So we have conversations with people where they say the same thing 6 times over and just refine the details ever so often. So we measure the size of the dip, from that we measure the planet size, and from that we can guess at the composition. If you get a really big planet, on the other hand, all the big planets that we've been able to measure the density of turn out to be gas giant planets. On the other hand, we see lots of these dips. And we see one of these dips once every orbit. Planet goes around once, it gets into just the right place, you see a dip, it goes around again, you see another dip. So basically, the time between these dips is the orbital period of the planet, the time it takes the planet to go around the star once, or the length of a year on that planet. Using a little bit of mathematics, which goes back to a fellow called Johannes Kepler, we can go from the orbital period of a planet to its distance from the star to the planet. So if you've got a short orbital period, you don't have a long way to go around, and so it doesn't take you very long. If you're Jupiter and you're a long way out, it takes you a long time to go around, so it takes years between the dips. If we have the planet-star distance, or the orbital separation, we can use that to estimate the temperature on the surface of the planet. Now, as I've said earlier, the estimate is a little bit naive. It doesn't take into account things like greenhouse effect or clouds or anything like that, but it gives you a first guess, so it's a good idea. So the things that we want to find out about our planets, what size it is, maybe what temperature it is, we can do this with the transiting method. Now, it's really not a lot. You would love to know so much more about these planets. You'd love to know, do they have clouds? Do they have oceans? You know, is there life on them? Can you see, are there radio signals coming from it, maybe? We can't do that. We spent an awful lot of money on this mission, and all we really get to measure are 2 features of the light curves. But from that, we can find out a lot of information about those planets. So this is the instrument we built. People have been doing this from the ground. They'd figured out they'd found planets this way. They'd figured out that it worked. But from the ground, it's very difficult to get the precise measurements you need to find really small planets like the Earth. So we went and built a spacecraft. We named it the Kepler spacecraft after Johannes Kepler, the fellow with the fancy equation. And this is what it looks like. There's a telescope here, mirror inside it. We've got solar panels on it, so we get some energy. And then we've got a little box down here which does all the complicated stuff. It's got CCD readout. It's got stuff to control the instrument. It's got stuff to save the data on board. It's got stuff to send that data down to Earth when we ask for it. Then it's got little things like star trackers to make sure we're pointed in the right direction. It's got small little things the spacecraft needs to have. It weighs about a ton. It's about 5 meters long. Put that in perspective. Here's 2 people posing as if they're putting the finishing touches to the spacecraft. 5 meters long is about the size of like a minivan, maybe an ice cream truck, something like that. So if we had this down on the Earth, that hole at the top is big enough for you to crouch down and crawl inside. Of course, the whole thing costs us about $600 million, so if we did get it back down on Earth, we're not letting you crawl around inside of it. So inside of it, since you're not allowed to get in, is remarkably boring. The guy who designed and got this spacecraft built and convinced NASA over a period of about 2 decades that this is what NASA wanted to spend its money on, a fellow by the name of Bill Barucki, he said, quite famously, that this was the most boring spacecraft that NASA has ever built. And that is a good thing, because if you have a boring telescope, you have very little that can go wrong. And this telescope is a long way away, and we're never sending a shuttle to bring it back to fix it, so we don't want anything to break in it at all. We basically have a mirror down here. We have our instrument up here, our detector. There's one more thing. There's a corrector up here to get the focus just right. And that's all that there is. The mirror is about yay big, 1.4 meters. So it gives you an idea, a sense of scale. It's built of a special glass which tends not to expand and contract with the changing of heating. Our major goal with this spacecraft is to keep everything the same. Nothing should change in the spacecraft as much as possible, including how much sunlight is landing on different things. It's an extraordinarily sensitive instrument. It's pointing. Sorry, I'm losing track of where I am in the talk. Let me go on. This is a detector. This is the extraordinarily sensitive detector I'm going to tell you about in a minute. It's basically a CCD camera like the one you have in your digital camera or in your smartphone these days. Each one of these little chips that you see here is about 2.25 megapixels. So on the scale of digital cameras, that's not very impressive. We've got 42 of them stuck together, so it's now a 100 megapixel camera, and I'll bet that beats anything any of you fancy amateur photographers have. In terms of technology, I think you'd all prefer if I didn't go too much into the details. If there are any amateur astronomers, I'm happy to tell you all the interesting things that we've done with this, which is different. But basically, all we have inside this camera is all we have inside this telescope. It's a digital camera, and we take really long exposures. We expose for 30 minutes. We collect all the light we are getting from the stars. We read it out. We save all that information on a hard disk. We take another 30-minute exposure. And we do that over and over and over again. We don't like to stop doing that because you'd hate to take a break to do something, and that'd be just the time when the planet passed in front of the star and you missed the damn thing. Now, it's not quite possible to observe for 100% of the time. We end up observing about 92, 93% of the time, because every now and again we've got to repoint the telescope to beam the data down to the Earth. But for someone who has done this myself, I used to do long time-based astronomy from the ground. And the real problem with doing long time-based astronomy from the ground, you want to look at something for a long time, is that every 12 hours the shaggin' sun comes up. You can't look at it anymore. And we went through all sorts of work. I worked on a collaboration known as the Whole Earth Telescope, which sounds really impressive. What it was, we got all our friends who were in different observatories all around the world to look at the same star. And the quality of the data you could get from that was much better than any one person could do from the ground on their own. But it meant that every now and again you'd have one site that you really need to get data from, and it got cloudy, and you were stuck. You didn't get that bit of data. So getting 92% of the data, for those of us who have experience, is a huge deal. We typically get 40% of the data if we were lucky. So this is a big deal. To give you an idea, it's an extraordinarily sensitive instrument, as I said. If you warm up this thing by a few tenths of a degree Celsius, you'll change the properties of the CCDs enough that we can detect it in the data. You're in quite a harsh environment in space. You've got the sun shining on you all the time. And if the sun shines on slightly different parts of the telescope at different times, that will change the heat distribution. That will change the amount of heat landing in each individual CCD and change the qualities of it and affect our data. We have these little gyroscopes in the telescope to help keep it pointed the right way. We have little heaters on the gyroscopes to make sure the gyroscopes don't freeze in space. One of the few things we have that moves on it. The heaters turn on and off every now and again, and we can see that in our data. It's extraordinarily sensitive, and so to get rid of as much stuff that can go wrong as possible, we've put it a long way out in space. I wonder if we could dim the lights. I've got a little video I'd like to show you to give you an idea of how far away it is. Now, please don't fall asleep. They're going to make this very dark for you. Okay, so here's the Earth. I hope you recognize that little island up near the top. So we're looking down at this like we're a satellite, and we're zooming away from the Earth. And these lines and the little labels that you can see up here, these are satellites. These are low Earth orbiting satellites that are looking down at the Earth. You can see coming around, if you look over here, there'll be a little thing which is called HST. That's the Hubble Space Telescope. So that gives you an idea of when they send the shuttle up to fix the Hubble Space Telescope, that's how far away from the Earth they got. It's a couple of 100 miles. It's really nothing. It's a very small distance. This animation, I should say, is made from a package called Eyes on the Solar System, produced by JPL. If you like the idea of flying through space yourself, I encourage you to go onto the web and check this out. It's really a lot of fun. As we zoom out, we're now getting to what are called geostationary satellites. These are satellites which are designed to sit over the same part of the Earth all the time. So they orbit the Earth once every 24 hours. These have to be at a very special distance away. It gives you an idea of the distance here. So your Sky TV satellite, that sits in the same place in the sky all the time. It's at about this distance. Off here you can see the Moon. The Moon is about 400,000 kilometers away, give or take. It's got 2 satellites around it called Artemis. You can see those up there as well. The Moon is the furthest that man has ever traveled. That's that distance. We're still going further out. Kepler is further away again. It gets a bit empty out here. After you get past the geostationary satellites, there's a few satellites which are on some very long orbits. But then there's not much until we get to a place called L1, or Lagrange 1. This is the point in the solar system where the gravity of the Earth pulling you back onto the Earth is exactly balanced by the gravity of the sun trying to pull you down towards the sun. That turns out to be a great place to put a satellite if you want to observe the sun. And you can see the satellite here called SOHO. It's sitting there at L1 doing just that. So as you can see, we've gotten really far away from the Earth here. And any minute now, we should see the orbit of the planet Venus. Here it comes. This gives you an idea of where the nearest planet is. It's a lot further away than the Moon. So you can understand when they're sending stuff to Mars how a much more difficult problem it is than sending stuff to the Moon. And here comes Kepler now. So here's the Earth, there's Kepler. We're a long way away. And the reason we're that far away is we want to get away from the Earth. We want to get away from all those other satellites flying around, all the junk they've left behind, reflections of light off the clouds would get in the way of our instrument. You've got the Moon nearby. It's a very complicated place. So what we did was we launched the satellite into an orbit which was ever so slightly bigger than the Earth's. If the Earth was, the distance from the Sun to the Earth was 1, the average distance from the Sun to our spacecraft is 1.02. So it's just a little bit further away from the Sun on average than the Earth is, which means it takes a little bit longer to go around the Sun than we do. So every year it falls just a little bit further behind. All right, could we turn the lights on before everyone falls asleep? Thank you very much. Okay, so we're flying around in space, in the solar system. All the time we're doing that, we're looking at the one patch of sky all the time. We're looking into the same part of the galaxy nonstop, the same set of stars. There's about 150,000 of them that we're particularly interested in. In terms of where we're looking in the galaxy, the galaxy has got these spiral arms coming out of it. We're on one of the spiral arms. Douglas Adams famously called it the unfashionable one. So we're looking not quite into that arm, but slightly above it. And the reason we're doing that is, like I said, we want to look at a lot of stars all at once. And so the best way to do that is look into the galaxy and not out of the galaxy. We don't look directly into the galaxy because there's too many stars, we'd get overwhelmed. If you're curious about where you should go at night, this is where in the sky that we're looking. So this is the summer triangle up here, and if I get this wrong, someone shout. So there's Deneb and Vega, they're in the summer triangle. Altair is the other one. Amateur astronomers, thank you. So here's the summer triangle. I'm an astronomer. I don't know the constellations. So somewhere here between the constellations of Cygnus and Lyra is the patch that we're looking at. That funny shape they have is showing the pattern that CCD is exactly where we're looking. To give a sense of perspective on that, if you take your arms like this, put them up in the sky like that, that's how much sky we're looking at. So it's quite a bit bigger than, say, the size of the full moon. Another way of putting that in perspective is, you know those beautiful pictures you see from Hubble of those gas clouds and those nebula and all the rest of it? If Hubble looks at a patch of sky that could be blocked out by a grain of sand held at arm's length. So this is a completely different design of telescope. Hubble zooms in on one really interesting thing in the universe at a time, whereas we're looking at a whole patch of the sky all at once. So this is more or less what the telescope sees. This is the first picture we took with Kepler, and everyone got really excited and we made a poster of it. Each one of these dark spots are the big bright stars in the field. Also the grey haze here are clumps of stars. This picture is too zoomed out to see the individual stars. Individual stars look a little bit like this on the picture. Now, because the spacecraft is so far away, we can't download one of these pictures every half an hour. It would simply be too much data. We can't do it. So what we do is we've looked at the 150,000 stars we think are the most interesting, the ones that we can get the most science out of. And we've basically done cutouts. And so we save the pixels around those stars, and we throw away all the other pixels. This is a terrible thing to do. It really is. All sorts of interesting things are happening on the stars that we're not expecting. But it's one of these trade-offs you have to do in science. In order to get the science that you wanted to do done, you had to give up on all the other science you wouldn't find. Now, it turns out that the stars are doing all sorts of things which are more complicated than we expected. And so even on the stars that we don't find planets on, we're doing all sorts of other science. I came from a conference just 2 weeks ago where we got 150 people together to talk about all the stuff they've learned from watching the stars flickering, getting brighter and fainter. These are variable stars, and if you have a variable star, you can figure out all sorts of properties of what's going on inside the star as well. So it's really been exciting. One of the things we've discovered is that our sun is quieter than usual. Most of the stars that are like the sun are actually more active. They've got more of these solar flares going off and stuff like that than our sun does. We don't know what to make of that yet. People are trying to figure out if this is a sign that our sun is unusually quiet and how that would affect the Earth, or if this is just the sun's in a quiet phase and it's going to come back to normal. It's nothing special. But when you're doing science, you find all sorts of stuff that you never expected to find. And so it's a terrible shame that we're throwing away all these pixels, but we're still doing really good science on the side at the same time. Of course, what we're really interested in doing is finding planets, and we've been enormously successful at that. We have found, as of December, I have to read this number because it changes, for us it changes every day, 2,326 planet candidates. These are things that, to the best of our knowledge, are planets. We accept the fact that in some cases we've probably got it a bit wrong. We've probably seen little dips which are due to something other than a planet, but these ones are the ones that we are most confident are actually real. What this little plot shows, and this is a really beautiful one, was made by a friend of mine at the Science Office called Jason Rowe. For every star that we found a planet around, he drew a disk which is, to scale the size of that star. And the black dots are the relative sizes of the planets around them. And I would dearly love to stand here and tell you something interesting about every single one of these planets, but it might take a little bit long, so I'll summarize it like that. It gives you an idea of the amount of work that has to be done on these ideas. So let me focus just on a couple of highlights instead. This is one of the early planets that we found. We called it Kepler 10. We've got every star that we look at has got a telephone number, like a 7 or 8 digit number to identify it. Of course, when you're talking about these things, it's very difficult to identify things by telephone numbers. This is why we give people real names. And so once we find something that we think is really interesting and we want to publish it, we give it a name which is Kepler something. So we have Kepler 1, Kepler 2, Kepler 3. We're up as far as Kepler 42 now. These are planets that we have confirmed are definitely real and are very interesting, and we published a paper about them highlighting one of their features. This is one of the very early ones. It's called Kepler 10. And you can see in this data, just like I showed you, you've got a star which is mostly flat. The brightness of the star is more or less constant. And every now and again, you see a little dip, one of these things. So we got interested in that. This is one of the early ones. And we said, well, the spacing between these dips is only 45 days. Put that in perspective, the closest planet to our sun has an orbital period of 88 days. So this thing is, give or take, twice as close in. But as we went looking in more detail at the light curve, we discovered that not only was there a planet there at 48 days, but in between these big dips, which I showed you earlier, are all these little small dips. These dips are 0.84 days apart. That's something like 16 or 17 hours. So here is a planet in orbit around a star, and 1 year on that planet is less than 1 day on Earth. So this thing has to be really close in. And if something's going to be really close in, it has to be really hot. It's so hot that nothing that we know of could exist as a solid there. Steel would melt, rocks would melt. Anything you could think of, the hardest plastics would melt. And so the surface of this planet, we give it to our artists for an impression, is probably one of molten lava. You've got an ocean of molten lava on the surface of this planet as it swings around its sun once every 16 or 17 hours. We thought that was really cool. So we released it, we got a press release, and so we got a pretty picture of it. This is why astronomers have press releases, so they can have pretty pictures to put in their slides. Another one we found, this is my personal favorite, we call this Kepler 16, or the planet is Kepler 16b. What we had was, instead of a planet going around a star, we had a planet going around two stars. So you have two stars, it's called a binary system. You've got the two stars that are spinning around each other like this. And around those two stars, much further out, a planet was going around that as well. Now this gets us really excited. It's got me really excited anyway, because when I was young and reading all those junior astronomy books, they always told me that you could never find a planet around a double star like that. It's impossible to form them, they're unstable, they'll soon get thrown out of the system. And so to find that they've gone and proven something wrong, it's always a nice little pat on the back. So one of those dirty little secrets about astronomy is you hear about the Higgs Boson, and everyone's celebrating that we found it. Some of us are actually happier when we prove people wrong. I don't want to slag off the Higgs Boson, that was a huge deal. I would have been more excited if they proved the Higgs Boson wasn't there, because then we'd have to scratch our heads and say, well, the theory that we have is wrong, so what actually is going on? And that would be exciting in its own different way. But back to Kepler 16, as we're sitting around and we're trying to do our press release and come up with our pretty pictures, we say, well, what would a sunset look like on a planet where that was in orbit around two stars at the same time? And it turns out we don't have to imagine what a sunset would look like on this planet, because George Lucas has already done it for us. And so we called the planet Tatooine. We got really excited about this, and we got in touch with Industrial Light and Magic, and you said, could we get George Lucas out for this? Could he make the presentation? Unfortunately, he was releasing the digitally remastered box set of something that same day, and so he couldn't come, but he sent like one of his assistants to come to our press conference. And afterwards, people said, they just released this planet to tie in with the box set re-release. You can't please some people. But while this planet is really cool, it's probably not like Tatooine. It's, if you compare it, if you plonk down the Tatooine system on sort of a scale model of our solar system, so this is where our sun would be, here's Mercury, Venus would be about here, and here's the Earth. On the same scale, here are the two stars. They're orbiting with an orbital period which is shorter than that of Mercury, and Kepler 16b is about this far away. So it's probably the temperatures on the surface of Kepler 16b are probably something around the same level as Venus. It's probably too hot for life to appear. Worse, this is almost certainly a gas giant planet, so it's got no rocky surface. So this thing is a really cool discovery, but when we show press releases of Luke Skywalker walking around in the desert, that's a little bit of a leap of the imagination. This is not a habitable planet. This is not a planet in the Goldilocks zone. We are finding planets which are much smaller than Kepler 16b. We're finding rocky planets. For example, in this one system, we actually found two of them. The system is called Kepler 20, and it has 6 planets in it, which is kind of cool, and they're all in very short orbits. The two smallest planets in the system are called Kepler 20e and Kepler 20f. And to scale with our solar system, here's Kepler 20e, there's Venus and Earth. Venus and Earth are about the same size. Here's Kepler 20f, it's ever so slightly bigger. So these are, in all likelihood, rocky planets. If these were in the right part of their solar system, they would probably be suitable for life. Unfortunately, as you can see up there, the orbital periods are, 6 days and about 20 days. So these things are in very short orbits again. They're whizzing around their parent stars. And so it's almost certainly far too hot for any life to exist on it, at least life as we know it. We are finding planets in the habitable zone. This is the Kepler 22 system. You'd think we'd come up with better names for these, wouldn't you? It's one of my long-standing, I've been working in this field for about 10 years, and whenever someone comes out with a really exciting discovery, they give it a really boring name, like Kepler 22. You know, why don't we call it Thor? Yeah, something like that. I know. Anyway, this is Kepler 22. Kepler 22 is a planet which is in orbit around a star which is almost exactly like our sun. It's the same size, it's the same temperature. So solar systems around there, the planets would have similar temperatures at similar distances from its parent star. They've drawn in this helpful graphic where the habitable zone is for our own solar system. It's about the same size for the Kepler 22 system. And Kepler 22 is just about hugging the inside of the habitable zone. So this is exciting. Here is a planet which is the right temperature to have liquid water on it. Liquid water, we think, is an essential criteria for having conditions suitable for life like our own. Unfortunately, Kepler 22 turns out to be quite a naughty little planet. It's got a radius of about 2.5 times the Earth. And like I said earlier, if we know the size of the planet, we can guess the composition, whether it's rocky or gaseous. That works for planets which are very small. We've worked out, we've confirmed these things with our techniques. We've measured the mass, which we don't get with the transit method. We find that all the really small things that are like kind of Earth size are rocky, sure enough. All the things which are really big are gaseous. This planet, Kepler 22, lies in that zone where we don't really have a lot of examples, and so we don't know if it is on the rocky side or on the gas side. And so while I say in the habitable zone, we're not really confident that it's a habitable planet, the sort that we'd kind of expect. So that's a quick run through. We're up to, like I said, 42 planets. I don't even have time to explain the highlights of them. But you might ask, why in my highlights I didn't say, here is a rocky planet about the same size as the Earth in the habitable zone, in the Goldilocks zone of its own star? And the short answer to that question is simply that we haven't looked long enough yet. And I hope with this fairly complicated slide to explain what's going on here. So you remember all your plots from junior cert maths? On the x-axis, we have the orbital period, how long it takes the planet to go around its star once, in days. We have this in a log scale, which is one of these absolute no-nos when you're giving public talks. You don't do log scales, that's complicated. But basically what it's saying is that every step you go to the right on this, you're talking about a step which is 10 times bigger. So over here we have 4 days, a step over the 10 days. Over here it goes from 40 days to 100 days. So what we're trying to do is compress the scale in so we get lots of information on the same plot. On the y-axis, we have the size of the planet relative to the Earth. So this bar here shows you planets which are about the size of the Earth. This shows you planets which are about 4 times the size of the Earth. That's Neptune-sized, to put it in perspective. And then 10 times the size of the Earth. That's Jupiter size. So based on our first 4 months of data, when we analyzed our first 4 months of data, here are the planets that we found in terms of the period that they have, how long it takes them to go around the star, and their size relative to the Earth. And you can see that we've got none down here, and none out here with periods of 300, 400 days, kind of like the Earth. And the reason for this is that we only detect these things when they pass in front of the star and we see a little bit of a dipping of a light. Our mission rule, our rule that before we publish these things, is that we have to see 3 of those dips to make sure that we're seeing what we think we're seeing, and we're not getting fooled by something else which is going on, which is strange. And so after 4 months of data, you can only see dips around stars with periods of about 40 days or less. Now, if you look closely at this plot, you'll see that we do have a couple of planets out here. This is where we got really excited by something and we broke our own rules. But it shows you our fundamental limit is it's about here. And if we could push out here a little bit, but we wouldn't be too sure of what we're doing. So that's 4 months of data. When we come along with 1.5 years of data, so this is the same plot. These blue dots are the same ones I showed you before. These yellow dots here are all the planets that we found after 18 months of data. And you can see that not only are we pushing out in this direction, we're pushing out to longer period planets, or out to like about 100 days, we're also pushing down to smaller planets. We're getting more sensitive to planets which are smaller size. And the reason for that is that you collect more and more data on something, you see more and more of these dips, it's easier to detect. As you can imagine, if there's only one of something, it's hard to see. If there's lots of them, it's easier to pick out. And so as we collect more and more data, we push out in this direction towards periods of 365 days or so. We also push down here, so we are more sensitive to smaller sized planets. And so we're pushing down and out. We haven't got out to this magic zone here, which is where we really want to go. Well, this is only 1.5 years of data. The third year of data got downloaded only about a month or so ago. And once we start analyzing that this summer, we hope to start filling in this region here. So it's a little disappointing, I admit. I brought you all this way out. I told you it's going to be a talk about finding Earth-sized planets, and we haven't found any yet. But bear with us. Give us a year, maybe 2 years. We hope to have a really big discovery. So what happens when we find an Earth? It's going to be really exciting for us, hopefully really exciting for you. But someone's going to ask the question, so is there life on it? Or can we live there? And we're going to have to say, we don't know. All we know is the size of the planet, and we have an estimate of its temperature. We can't tell you anything about mountains, oceans, clouds, anything like that. And that's going to be really frustrating. Think about it. Here's a planet, it's just like the Earth, except we don't really know. But we'll never be able to see it. In order to find out, are there mountains or oceans or atmospheres, you're going to actually have to directly detect that planet. You're going to have to take a picture of that planet and not just its shadow as it passes in front of the star. Now, I've said this is impossible, but scientists always like to work on questions that are impossible, and people are starting to make progress on this. So what I'm showing here are possibly two of my favorite pictures from astronomy recently. These are two stars around which people have managed to directly detect the light from the planet. And they do that by very carefully blocking out the light from the star, so that very faint light from the planet, that very tiny contrast, actually becomes detectable. And so what we've done up here with this very colorful ball is they took this picture of the star in 3 different filters, 3 different colors. These aren't colors the way we normally think of them. They're in the infrared, but they color them red, green, and blue so they can keep track of them. They blocked out the light as much as they can, and this is the light which sort of filtered through. Around it, you can see these 3 small dots. These are planets. This is, if you've not seen these pictures before, this is the first time you have ever seen light from a planet around another star. I certainly think it's cool. This one here is the same idea, except around this star, they've blocked out the light from the star almost completely, so they've marked in where the star is with a little dot. And this star is different in that it doesn't just have planets around it, it has this enormous ring of dust. If you think of like the asteroid belt we have around our own solar system, well, think of that spreading through the entire solar system. It's very flat, it's very smooth like in thickness, but it's enormous. It stretches from very close to the star all the way out to many, many hundreds of times, many times further out than Pluto is from the sun. And what was really cool about this is people were taking pictures of this dust disk for a long time, and they noticed that it had this pattern here. It seemed to have this ring structure in the disk where there was more dust than there was elsewhere. And someone worked out the numbers and said, there's probably a planet there. If you had a planet there, the little gravitational pull of the planet and all those dust particles would sculpt this disk into something like a ring. So someone went out and they looked really hard, and sure enough, they found this thing moving through the system. So this is, and these 2 images came out in the same day. This is the second time you've seen light from another planet around light from a planet around another star. Now, while this is really cool, I don't want to say anything bad about this at all. It's a big step from there into directly detecting the light from a planet like the Earth. To give you an idea of scale, this closest planet here, which is right inside the cloud of the light that they couldn't quite block out, is 30 times further away from its parent star than the Earth is from the sun. It's also, and they're not quite sure, somewhere between 5 and 7 times more massive than Jupiter. So these are really big planets. They're really far away from the star, where the contrast problem is not as severe. And so in order to go from detecting this thing to detecting the Earth, you're going to have to improve your ability to do this by roughly a factor of 1,000,000. And improving anything by a factor of 1,000,000 is a really hard thing to do. Some would say impossible. That's not to stop people from trying. And so this is a couple of sketches. This is ideas that people have of ways that we can reduce the contrast between a planet and a star by the necessary factor so you can directly detect light from the Earth. So this thing here is called TPFC, or the Terrestrial Planet Finder Coronagraph. And the idea here, and I'm going to simplify it grossly because it is actually genuinely very complicated. One of the few things in astronomy which is complicated is coronagraphy. The idea here is that you put a little mask inside your telescope which is going to block out the light from the star, but not block out the light from any planets which are nearby. To give you an idea of how much more complicated it is than I'm suggesting, this is the shape of the mask that they want to use. So the white bits is where they're letting light through, and the black bits is where they're letting light stop, or where they're trying to stop the light. And the reason it's this shape has got to do with the fact that light actually behaves like a wave. It's almost like a wave in the ocean. The mathematics you use to describe it is the same. And when you're trying to block out light in certain ways, you can exploit the properties of light being a wave in order to do it very effectively. But it is quite complicated. It's also going to be extremely difficult to build. They don't know how to build this thing yet, to the tolerances they need to block out the amount of light that they have. They also don't think they can hold it in place inside the spacecraft in exactly the exact tolerances they need in order to have this thing stare at a star for something like a day or two and be able to work its magic. So this is a hard problem. People are still working on it. Another idea people had, which I've always thought was really cool, was the TPF. This is actually called Darwin, I'm sorry. And the idea here is it's exploiting the fact that light is a wave, and it has 6 telescopes free-flying in space, and it moves the distance between the telescopes just by very small amounts. And as the light comes into each telescope and is then combined in a certain place, if you move the telescope into just the right position, you can block out the light just from the star and not from the planets. This is enormously difficult to do. You have to hold these telescopes in just the right place to within 1/1000000000th of 1 meter, which is something we don't know how to do. So these two ideas, it was quite funny because I was a lowly graduate student when this was coming out, and people suggested this idea. They said, we should build an interferometer in space to detect Earth-sized planets. And everyone said, that's a great idea, you should go do that. And they came back a few years later and said, well, technically this turns out to be really difficult. So someone else stands up and says, I know, we don't need to build an interferometer, we can build a coronagraph. Coronagraph is really easy to build compared to interferometer. So everyone says, that's a great idea, go build a coronagraph. And they came back a few years later and said, turns out this is a little bit difficult to do as well. So when this one failed, someone came out with another idea, and this is called the TPF-O, or TPF occulter. And the idea is that if you take this mask, and instead of putting it inside your telescope, you make it a whole separate spaceship which is flying about 1 million kilometers away from the telescope. The physics, the mathematics work out the same. You can block out the light from the star, leave the light from the planet, but you don't have to build anything with anything nearly the same tolerances. And so they come up with this very fancy petal shape, which is apparently the optimal way to do it. The problem with this, twice bitten, 3 times shy, is that these little spikes here that you can see in this little artist impression, they turn out to be very important for blocking out the light the way that you want. And they're going to be very flimsy. So if any sort of a meteorite is flying around in space and whacks into one of these things and breaks it off, you've ruined the telescope. And these things is going to cost something in the region of $1 billion to $2 billion. And so you don't want to have such an easy way of it failing like that. But people are thinking about this. It's not a solved problem. And it's not inconceivable that within our lifetimes, we will be able to see the light from a planet like the Earth and start asking questions like, what's on that planet? So to summarize my talk, the best place to look for life is on planets like our own. That's what we're doing with Kepler. We're out there, we're looking for transits. We're not looking for the planets themselves. We're looking for the shadow as the planet passes in front of the star. We haven't found any Earths yet. We've found thousands of planets. A lot of them are really exciting. They're all really interesting. But we haven't found what would be the headline, the planet like the Earth. But we should do soon enough. If you found this interesting and you're still awake and you want to find out more, we of course have a website. It's kepler.nasa.gov. NASA being NASA, we actually have 2 websites, one of which we run and one of which we don't. The other one is nasa.gov/Kepler. The information between them is not always in sync, so if you really want to know more, go read both of them. If you're below a certain age and you're into the Facebook and the Twitter and all that sort of stuff, we are on Facebook, we are on Twitter. Those are the addresses. If you are on Facebook and you like to follow this stuff along, stuff gets announced all the time that doesn't make press releases. And so we say, we found this thing that's kind of cool. And so you can keep track at a much lower level of detail than you will from watching the news by following us along this way. If you thought this was fun and you'd like to try your hand in it, I strongly recommend you check out planethunters.org. These people, just as a hobby, have taken all our data that's public, They've put it on a website in such a form that ordinary people who have no mathematical ability, no knowledge of, haven't done any physics in secondary school or anything like that, where you can just look at these light curves and try and find these dips. And their argument is that if there's thousands of people thousands of people like you out there looking for these dips, you will all collectively do better than the smartest computer program that scientists can come up with to find these things. And they may well be right. So I would strongly encourage you, if you have afternoons where you're saying, I'm just sitting around wasting on Facebook, I wish I could do something more useful with my procrastination, go look for planets. The same people who do this, they're an organization called Zooniverse. If planets aren't your thing, they have all sorts of projects like this. They call them citizen science projects. You can help them count craters on the moon. You can help them classify galaxies out there in deep space and help the cosmologists find out how old the universe is and how things formed. They've got all sorts of fun things you can do, so I do encourage you to check them out. If you like the idea of helping science, but you don't like the idea of doing work, SETI at home is for you. This is just a screensaver. You download this onto your computer, and when you're not working at your computer, when you're getting a cup of coffee or something, it goes onto the internet and it downloads some data taken by a radio telescope out in California. It downloads this data onto your computer and it analyzes it for signals which are artificial, which are not man-made. The idea is that they're pointing at all the stars that Kepler has found planets around, and they're listening for radio signals. And so they get all this data. They can't possibly analyze it all themselves, so they've farmed it out to people who have computers that aren't doing any work right now. So all you do is you download this, it analyzes the data. If you find that signal, you're going to be world famous. And if you don't, you've been helping around. These people, of course, once you get one of these good ideas, they're utilizing people's spare computer cycles for lots of other things. You can also go on and do things like help with protein folding problems, which I'm assured will help us someday find the cure for cancer. So if your computer is sitting there just showing those flying windows, go download one of these things and put it to use. If you're more practically minded and you want to go out and do something yourself, you don't know where to start it, please get in contact with irisgastronomy.org. This is the Federation of Local Astronomy Organisations in Ireland. They'll be able to hook you up with your local group of people who can take you out and actually see the planets in our own solar system. And I'm willing to bet that there's a fair fraction of the audience here who have never actually seen one of the other planets in our solar system. Go out, find the telescope and look. They're amazing. And of course, if you're really hardcore and you like, stabbing yourself in the eye with toothpicks and stuff, you can go download the Kepler data itself. As of October, we'll make it all public. It's in very unfriendly very unfriendly formats, which are designed for astronomers. But if you know what you're doing and you want to tackle these problems, NASA is a terrible organization in many ways, but one of the things that they are really convinced about is that everyone should have access to their data. If they take data, anyone who thinks they know what to do with it can go and use it. And so I make a plea, if there's anyone out there who loves analyzing signals and stuff, go take a look. I'd like to thank you all for coming. That's the end of my talk. I'd especially like to thank the Science Gallery for bringing me here and then ambushing me with questions about Higgs bosons, of which I know nothing about. In particular, I'd like to thank Sean O'Boyle for that and Ian Brunswick. Both of those were instrumental in helping get this talk organised. I just showed up and gave it. It was absolutely great. I'd like to thank Al White, who's sitting out there somewhere, for making the introductions so I could meet these people and come here. I'd like to thank my mammy for driving me here and my daddy for doing the babysitting so I'd be able to come out. And with that, I'll open myself to questions. Sure.
Thank you, Fergal. That was fantastic. I really enjoyed that, and I'm sure I speak for everyone when I say thank you for telling us about Kepler. We have time for some quick questions if anyone wants to ask some. I think Debbie and Sarah will be going around with roving mics. There's just one down here. In the meantime, I just want to say that the next talk in the SFI speaker series is next Thursday. We have best-selling author and string theorist Brian Greene here at the gallery, which should be a brilliant talk. He's over here for ESOF, which is that fantastic, massive science conference that's a big deal for Dublin. It's happening next week, and it's the reason that we've all been celebrating Dublin as a city of science for 2012. So check that out. I guess if there are no questions straight away, I'd like to ask what is... Sorry.
Brian Greene is a huge deal.
Yeah.
I am embarrassed to be talking in the same series as Brian Greene. If you have any chance of getting out to see him, he's an absolutely amazing speaker. It's your best chance to ever understand quantum mechanics, string theory, Higgs bosons, all the rest of it. Go check him out.
That's the plug that I couldn't give. So. I guess I'd like to ask first, how long is the expected lifespan for the Kepler Space Telescope? How long do you think it'll continue to gather data?
That's a budget question. Okay. We were originally, it was great. Kepler was a 5-year mission to seek out new worlds. Then budget cuts made it a 4-year mission. Further budget cuts made it a 3.5-year mission. And the logic of that was, well, that's long enough to see a planet go around 3 times, right? We go out, we discover that some of our estimates of exactly how noisy the stars are were optimistic. And so we went back to NASA and we said, look, we're doing all this great science, we're finding all these planets, but with 3.5 years, we'll probably find a couple of Earths, but we won't find them all. We need to go back up to a longer mission. And so NASA has this thing called senior review, where all the telescopes say, look, we've done an absolutely great job, but you give us a bit more time, we'll do something even cooler. And they sit them, a bunch of scientists sit down and rank these proposals and say which ones should be given more time. We were given 4 more years. And we all went, yay, we got 4 more years, we can do all sorts of cool stuff with 4 more years. It might not last. They only gave us money for 2 years. And they said, in 2 years, you're going to have to go back to the well again and say, you need the money for the next 2 years. We think you're great. We think you should get money for 4 years, but we only have money to give for 2 years. So it might become a 5.5-year mission. It might become a 7.5-year mission. Eventually, like I say, the telescope is drifting further and further away. And so the amount of data we can get back to the Earth gets less and less every year. And so we'll start dropping targets until the signal from the telescope is too faint for us to detect. And after that, we'll run out of fuel. After about 10 or 11 years.
Okay.
So that's what we have.
Fingers crossed it'll last. Any questions?
Is this on? Is it? Yeah.
Yes.
Sorry, just a quick one. Well, on that, have you guys ever thought of crowdsourcing money? You know, like Kickstarter and stuff like that? I'm sure people will be happy to donate.
I was talking to a friend of mine. So that's actually a really complicated problem, and we have thought about it. But you're getting into government rules about release of property. So there was one telescope, which is in one of those low Earth orbits, and a whole bunch of people who were Stanford alumni said, well, look, we're multimillionaires. It's only going to cost $1 million a year to keep going. Let's just buy it. And, you know, the scientists said, oh, that's a great idea. Let's do it. And the lawyers said, well, if it crashes, you know, who has to pay up? And so there's strange problems like that. It's not a lot of money. Like, we're talking about $20 million a year to keep this thing running. You're asking the wrong person, unfortunately, to get a straight answer to that. If we have thought about it, we didn't get very far with it, I think, is the short answer. Yeah.
The question was about the mask and putting it up into space and stuff, you know, to get rid of the interference. And you were saying how it's susceptible to, you know, like bits of grit or whatever, if it knocks one of those flimsy things off. Could you not virtualize it and actually, you know, just imagine it was there, if you know what I mean?
It's amazing what you can do with virtualization. What would happen if something was there? It turns out at some point you need to put hardware in place. And you need to put hardware that has certain specifications in place. And you know, once you put that hardware in place, there's going to be a lot of mathematics going on to untangle what you get out the other side. But eventually you need to put something up there. If we could do it all on computer, we would. And we do as much of it as we can on computer, but there's a limit. Okay.
Any other questions? There's just one here.
I was wondering if you had any opinion on the Fermi paradox, or if you had a personal answer for it.
Okay, so the Fermi paradox. Enrico Fermi was a gas character. He was the first person to produce a nuclear power plant. Some people claim he did it by accident. He worked on the Los Alamos project to build a nuclear bomb, and he used to ask people questions. He used to just sort of throw them out there to make people think. One of his famous ones was, how many piano tuners are there in Chicago? You know, what? And what he wanted to say was, well, look, okay, the population of Chicago was like 1 million at the time. And so you've got 4 people in every house, so you've got this many houses. This many fraction of people buy pianos. It takes a piano tuner. A piano tuner can tune 10 of these things in a day when you take into account getting from house to house. So you can say, how many piano tuners do you need to keep all those pianos tuned? That was his way of thinking. He was a really smart guy. And one of his questions was, look, there's those millions of planets out there, at least you claim. If they're all there, how come none of them have contacted us yet? And there's no good answer to that. One answer is, we are alone. There's no one out there talking to us. Another answer is, there's life out there, but it exists in this technological state where we have things like digital watches and big radio antennae for such a short amount of time that the chances of us finding of two of these things appearing nearby are pretty low. Other people have more fanciful ideas, like we're being kept in quarantine. I hesitate to give an answer because it's an opinion. My opinion is somewhere around the second one. The chances of us finding someone nearby who's actively communicating with us is actually quite low. And one of the things that someone has pointed out to me recently is that when people were setting up the SETI project, where they would build these big telescopes to listen out there, they were doing our calculations of how many you might find and what you'd be susceptible to based on those big television antennae that we had, which were beaming out television signals all over the world. But now we have satellite TV. So we don't build those big, strong antennae anymore. We beam the information up to the satellite, and then it's beamed back down. So the noise, the radio noise coming off the Earth, is much quieter. Even though we've still got a technological civilization down here, we wouldn't be detectable to very many people because we're not beaming out those signals anymore. And so that's the best answer I have for you.
That's a good answer. Any more questions? If not, I'd like you to join me in thanking Fergal again for joining us this evening, and thanks to all of you as well for coming tonight.